Hi, my name is Galindez, and I am a PhD student at Leuven in Belgium. And today I will present our work on discriminative bias for learning probabilistic sentential decision diagrams. This is joint work with Wannes, Meert, Nimish, Shah, Broeck, and Marian Verhelst. So I will start by introducing our motivation and objectives, and then I will briefly discuss some relevant background concepts. Then I will introduce the main contribution of our paper, and I will finalize this presentation with some experimental results and conclusions. The motivation behind our work is threefold. First of all, probabilistic inference has already proven to be well suited for resource-constrained embedded applications. And this is particularly true for probabilistic circuits because they have been able to successfully balance inference efficiency with expressiveness while remaining robust to missing data. And this is because they are often learned in a generative manner. However, the same robustness often means that their discriminative performance is not very competitive when compared to other classifiers. And so the goal in this work was to come up with a learning strategy that would be able to improve the discriminative performance of probabilistic circuits while keeping their robustness from generatively learning them. So probabilistic inference allows us to answer a number of queries given a probabilistic model of the world defined over a set of random variables, such as, for example, what is the probability that it is a sunny day and I see a rainbow? Or what is the probability that it will rain given that I don't see a rainbow today and it is the month of January? Or something more involved like what is the month where it is more likely to have days where it is both sunny and rainy? And so several of these queries are computationally expensive, and they even become intractable for certain families of probabilistic models. But what do we mean by tractability? Well, in the context of probabilistic inference, a query is tractable if and only if exactly computing it runs in polynomial time. Naturally, there's an inherent trade-off between how tractable a model is, or how many tractable queries it supports, and how expressive it is. But there is a class of models called probabilistic circuits that have been able to successfully manage this trade-off by combining the power of logic and statistical learning, among other desirable properties. And basically, a probabilistic circuit is a computational graph that encodes a probability distribution over a set of random variables. In this paper, we focus in particular on the probabilistic sentential decision diagram, or PSDD. And a PSDD is basically a probabilistic extension to sentential decision diagrams, which represent Boolean functions as logic circuits, as we can see in this example here. And as such, they are capable of representing joint probability distributions over random variables. For example, this PSDD here encodes the same distribution as the Bayesian network to the left. And in particular, the inner nodes of a PSDD alternate between OR and AND gates, and the root node of a PSDD must always be an OR gate. And finally, the leaves encode distributions over the input random variables. Within a PSDD, the combination of an OR gate and its AND gate inputs is called a decision node, where the left variable or the left set of variables of the AND gate is called the prime, and the right one is called the stub. And actually, this organization of variables into primes and stubs is driven by this binary tree called a variable tree, or V tree for short, in such a way that each of the internal nodes of the V tree corresponds to a level on the PSDD. Finally, the edges of the decision nodes are always annotated with a normalized probability distribution. So PSDD have a number of desirable properties that enable tractable inference on them, the most important being decomposability and determinism. I won't go into detail for the sake of time, but I encourage you to look into this reference for more information. And these properties essentially allow to encode the following distribution over each decision node. Note that the distribution decomposes into independent distributions over the prime and the sub variables. In fact, in general, in any node n, the prime and the sub variables are independent given the prime base, denoted by P here, which is basically the support of that node's distribution and can be written as a logical sentence. So in this example, the prime variable is rain and the sub-variables are sun and rainbow. And so the base of the left AND gate is rain is equal to true, whereas the base of the right AND gate is rain is equal to false. And this allows to encode the distribution over this decision node in this compact way. Now, the technique we propose in this paper is an extension to the Learn PSDD algorithm. This technique learns the structure of the model incrementally and fully from data. So it first generates the B3, as I said, from data by minimizing mutual information among the sets of random variables available. And then it iteratively applies the split and clone operations, which sequentially try to improve the log likelihood of the model given data. And so in practice, this translates to sequentially or iteratively increasing the complexity of the model and thus improving the performance in terms of log likelihood of the model. Now, the contribution we make in this paper is introducing a discriminative extension to the Learn PSDD strategy. As I mentioned at the beginning of this presentation, our paper focuses on classification tasks. So given a feature variable set F and a class variable C, the classification task can be stated as the following probabilistic query as defined by the Bayes theorem. And so the problem of performing classification with models generated by the Learn PSDD is that this strategy actually remains agnostic to the classification task because it tries to optimize for log likelihood of the model given all the data. And so in this example, we can see that the learner will most likely not be able to figure out that the features should depend on the class variable. And thus, this conditional probability is not going to be expressed in by the Learn PSDD. But actually, this conditional relation has a big impact on the classification task, as has been often observed by Bayesian network classifiers, which, despite their simplicity and the fact that they are also generative models, have proven to be very good at classification tasks. And this is exactly because they explicitly encode this relation between the features and the class variable. And so in order to enforce this relationship in the Learn PSDD, we introduced this D-Learn PSDD technique, where D stands for discriminative. And first of all, we generate this special V3 where we force the class variable to be the prime of the root node, and we let the rest of the features be the sub of the root node in such a way that the Learn PSDD can be capable of learning to condition the feature variables on the class variable. Now, by default, the Learn PSDD algorithm initializes on a fully factorized PSDD like the one shown here. But if we do the same, even with the special V3 over here, and even though the class variables are at the top of the PSDD, we cannot ensure or guarantee that the conditional relation we're interested on will actually be learned. In fact, we show in the paper that in the worst case scenario, even after many iterations, feature variables will still be independent from the class variable. So what we had to do instead is to explicitly encode this relation or this constraint as a logical formula and set it to be the base of the root. And this allows us to initialize the learning algorithm on a PSDD that already encodes the structure of an A Bayes classifier. And the Learn PSDD ensures that this base of the root remains unchanged, meaning that the conditional relation that we initialize the learner on will always be held. So in the paper, we run experiments on 15 UCI datasets and report 5 cross-fold validation accuracy, as well as model size in number of parameters. We compare the performance of our approach with that of traditional PSDDs, naive Bayes classifiers, tree-augmented naive Bayes classifiers, and logistic regression. And first of all, we see that our method always outperforms the traditional Learn PSDD approach. And moreover, it does better than the other classifiers in 10 out of the 15 datasets. Finally, we show that our algorithm remains robust to missing data. So in this figure, the shaped markers show accuracy under the full feature set, whereas the flat ones show accuracy after subjecting the classifiers to random feature failure. And in the paper, you can see that the D-learn PSDD, which is marked in blue, achieves best accuracy even after feature failure on most of the datasets. So to conclude, we introduced a PSDD learning technique that improves classification performance by introducing a discriminative bias. We ensured robustness by exploiting the generative learning strategy that we started from. And finally, we can see that the proposed technique outperforms purely generative PSDDs in terms of classification accuracy and the other baseline classifiers in terms of robustness. Thank you very much for your attention. I hope you enjoyed this presentation, and please do not hesitate to contact me if you have any questions.